So, welcome to the first ever AlCoVR, which is the Algebraic Combinatorics virtual reality workshop. We're going to be hearing a lot about dynamical algebraic combinatorics from Bruce Sagan here. Please let us know if you have questions or issues technically that come up. You can raise your hand physically, you can raise your hand in the actual classroom. Of course, you can ask Bruce questions with using the raise the hand feature and everything. This should hopefully feel like a real classroom experience. So we'll see how this works. We definitely want your feedback afterwards. We're going to have a feedback session after all the sessions today in Zoom, so we can just chat about how it went. And I'm really excited to be here with all of you and excited to hear what Bruce has to say. So we're going to have Bruce take it away. I'm going to go take a seat here. And when I do, we'll start the conference. It's not, now it's not letting me click on the right thing here. Let's see here. Oh, I have to press. That's what I have to do. There we go.
Okay. Maria, you're still in front of the Blackboard.
Yeah, it's 1 second. Okay, now I'm seated.
Great.
And now you can get started. There we go.
Okay, well, thank you all for coming. It's great to be here. And again, just to reiterate what Maria said, if at any point you have questions about what I am saying, please raise your hand. I want this to be as clear as possible. So, oops, you're back in the Blackboard again.
Sorry, I was trying to record. Let me try one more thing.
Sure. Oh, and while she's waiting, while we're waiting for Maria to get back to her seat, I also know that my handwriting isn't great. So if you can't read something, also please ask. I'm happy to answer all questions, mathematical or just in terms of being able to understand what I'm writing.
Sorry about this. Am I still at the whiteboard?
Yes.
Okay. There we go. Sorry about that. Okay, take it away, Bruce.
Okay, sounds good. So as was said, we're going to be talking about dynamical algebraic combinatorics. And my pen doesn't always work very well, but we should begin in the first section about talking about what really is this thing. What is dynamical algebraic? And usually we just abbreviate that to DAC. Okay. So here's the basic setup and some of the basic questions that we ask. So let G be a group. We're going to assume it's going to be finite. You can do things with infinite groups, but for starting out, let's keep things nice and simple. And we want it to be acting on a finite set. Set X. And again, we could do things infinitely, but let's keep it simple. So here's some basic questions that people ask in dynamical algebraic combinatorics. First of all, suppose that the orbits of G's action are, say, script O1 through script OL. We just want to know, right? We're counting things. We'd like to know their cardinalities. What are the cardinalities So I'm going to be using this little hashtag symbol for cardinality. And if we can't tell you the cardinalities exactly, we'd at least like to know some things about, oop, Maria, you're back.
It's just recording, and it won't let me record unless I go to. I'm gonna permanently be at the desk now.
Okay, sounds good. Okay, so hopefully that's pretty clear. Very simple question to ask. Here's something that's a little bit more complicated, but also extremely interesting. So we need a definition here. So suppose we have a statistic what is a statistic going to be for us? So a statistic on our set X, so that's going to be a function that takes each, say it's ST, it's going to take each element of X and give me back a non-negative integer. So I'm going to use this math boldface N for the non-negative integers. Can everybody read what I'm saying, even with Maria there? Okay, good. Question, great. I saw a thumbs up, excellent. Okay, so we'll say that this statistic is a homomessy. And this comes, the two Latin roots here. Homo means same. And messy here means middle. So it has the same middle, and that'll become clear once I've defined this precisely. Another term that is used is that it is homometric. If the average of this statistic, so what's the average going to be over an orbit, right? Well, you're going to take all the elements X in a given orbit and sum their statistic values, and then divide by the cardinality of that orbit, right? So you add up all the statistic values on the orbit. I see heads nodding. It's clear with this, and this is clearly what you normally do when you're computing the average, like the average score on a test or something. What we require that this is the same for all orbits. So it does not depend upon which orbit you choose. You get the same average everywhere, right? Which is kind of cool.
Bruce, quick question.
Yes.
Is that like homomassic instead of homometric?
Oops. Yes, it definitely is. And thank you for let's make that correction. Yes, no. Homometric means something else, which we'll get to later. This is homomessic. Thank you. Anything else which needs to be corrected? Okay, if we want to be specific about what this constant is, so if this constant average is, say, some value C, we say that the statistic is C-messic. So it is always, we're telling you here now exactly what the average is. It's always this C. Okay, any questions so far? Great. So was that a hand, Nicholas?
Yes, sorry, I was trying to unmute for a second. Are the orbits indexed by the elements of our finite group or our finite set?
The set, because so remember, when you have a group acting on a set, the orbits are formed by so to find a particular orbit, what you do is you take an element of a set, and then you act on it with G, with all the elements of G. That gives you a bunch of other elements of the set. Those all go into that orbit. So that's how you find an orbit. And so they're not really indexed by the element. You can, but you get into this thing just like when you're dealing with subgroups of, you could orbit it. Let's just say it's that. And of course, each element of the set gives you an orbit, but two orbits could be the same for different elements of the set. Other questions? Okay, so that's another thing. Now, we're going to be particularly interested in not just arbitrary groups, but cyclic groups. Okay, so there are some other questions that you can ask if the group is cyclic, specifically for the cyclic group. So if G is a cyclic group, say that G is generated by some element in the group gamma. Okay, so this is what I'm going to use the notes, pardon the barking dog. I don't know whether you can hear it or not, but that's life with a dog. I'll use these brackets for meaning generated by. Then you can also ask a couple of other interesting questions. First of all is, what can be said about the order of that group element, that generator? Right? So remember, the order is just the smallest power of that generator that gives you the identity element of the group. And so since G is generated by this is also, you could think of this as just the size of the group itself. So that's the order. And then something more specific that we been very interesting to Algebraic combinatorics lately, something called the cyclic sieving phenomenon. So for that, we're going to need a polynomial. So let f of q be a polynomial. In a variable q. And a bit of notation, if I take a group element G, we're going to consider the fixed point set. So I'm going to denote this by x to the power G. So remember, what's the fixed point set? It's the set of all elements little x in my set X that are fixed by the action of that element G that we picked, right? They are not sent anywhere. I just put all the things that stay exactly the same. Then we say that this triple consisting of X, the group, and this polynomial exhibit cyclic sieving phenomenon. And of course, that's much too much for me to be writing out each time, and I'll usually just abbreviate that to CSP. If for all group elements, if I calculate the cardinality of the fixed point set, that is gotten by taking our polynomial and plugging in omega where omega is a root of unity. That has the same order as our group element, right? The roots of unity form a group. You can talk about order. Now, this is kind of amazing, right? Because remember, omega is a complex number. A lot of roots of unity. We're plugging it into this polynomial, and we're supposed to get out the number of fixed points, which is a non-negative integer. If you plug an arbitrary complex number into a polynomial, you do not expect to get a non-negative integer out. But this phenomenon turns out to be everywhere. It's really common. So we'll see some very nice examples of this. Yes, Aditya.
In this case, is G cyclic or any group?
Yeah, no. The C and D are both for the cyclic case. Okay. Yeah. There are generalizations of the cyclic sieving phenomenon to non-cyclic groups. They don't seem to be as abundant, but they exist. But again, we're trying to keep this in the simplest possible case, since you're seeing it for the first time. Other questions? Leah, is that a no? Okay, yeah, it's hard to tell sometimes, and then people are getting used to this stuff. Okay, so let's get. Yes,
There's
Robbie.
a question for Robbie.
Yeah.
I had wanted to ask, it seems like if you have the CSP, it means that the size of x to the g depends only on the order of that element. Is that a general fact, or is that something that only some?
No, this is something very specific.
Okay.
This is something very specific. Yeah, so this is even more amazing. Other questions? Okay, well, let's get to something concrete. Let's get to an example that we can put our claws into. So let me just, I have to adjust. So this is going to be one of our big examples. It's a really easy example, which makes it nice, but it's also going to be the one that we can use a lot. And this is going to be bit strings. Okay, so just to set up some notation, script B and K is going to be the set of all bit strings B equals B1 through Bn. So B is going to be my notation for a bit string. The actual bits are going to be B1 through Bn. So right, the N and BNK tells you how many bits there are. So bits, right, remember, so each BI is 0 or 1 for all I. And what the K is doing there is telling you how many 1 bits there are. I, 1. It's really concrete. Suppose we look at B42. What's that going to look like? So 4 bits, 2 of them are zeros. Sorry, 2 of them are 1s, which make the other 2 zeros. So that's just going to be this set. They're the 6 ways of doing that. Okay, clear what these bit strings are. Great, great. So we now need a group to act on this. So let's let G be the group generated by the following rotation operation. So rot here stands for rotation, and what rot does to a bit string, it's very simple. It takes your bit string and it moves the first element to the end, right? Rotates it to the end. So you now start with B2, finish off by putting very simple sort of thing. So let's look at the orbits here. So going back to our example, so for example, let's take the orbit that contains 0, 0, 1, 1. Okay, what's the next thing? If I act on that by rotation, what's the next string going to be? Say
1, 0, 0, 1, 0.
Okay, so we're taking the first element, which is a 0, and rotating it to the end, which will give us a 0, 1, 1, 0. I think I heard somebody say that. Clear what's going on? Okay, so what does the rest of this look like? Now you rotate the other 0 to the end, that gives us this. Now we rotate the 1 to the end, that gives us this. And now when I rotate that 1 to the end, I'm back to where I started. Everybody agree that that's one of the orbits? Good. Seems to follow, which is excellent. But we have another orbit because, right, we've got 6 elements. Which ones didn't we get? Well, we didn't get this string, 0, 1, 0, 1. Now when you rotate the 0, you get this. And now when you rotate the 1, you get back to where you started. So this orbit only has 2 things in it. Okay. Questions about this? Any questions? Good. So let me then prove our first proposition. It's fairly simple, but it's okay. So we're going to answer some of those questions that we had before for this nice action. So for the group generated by rotation on BNK, first of all, what's the order? Well, it's kind of the obvious thing. It's going to be n for most of the values of k, and it's going to be 1 at the extremes. K is second thing, so that tells us about the order. We also want to know about the orbit sizes. And one thing we can say is that the orbit size always divides n for all orbits. So this vertical line here means divides evenly as integers. Okay. clear what we're trying to prove? Okay, well, let's prove it. It's not hard. Okay, well, take care in this first one, we'll take care of the trivial cases first. If k is one of the extreme values, how many bit strings do we have? One. Yeah, exactly. Ben is holding up the right number of fingers, right? If there are either no ones, in which case it's all zeros, or there's all ones. So there's only one element. So you only have one orbit of size 1. I mean, there's nothing else you can happen in this case. So in this case, cardinality is k is 1, and you're done. So what happens in the non-extreme cases? Well, clearly, I think what's going to happen if you rotate n times? Get the string back, right? You've got n bits, you've rotated them all, you'll get back to the original thing, okay? So this is going to have to be, if I rotate n times, I will get my bit string back, okay? Does this prove that its order is equal to n? Not quite. It only proves that the order divides n, right? This is some power of rotation which gives the identity, but it may not be the smallest power that gives the identity, right? So this implies that the order of rotation divides n. How do can we get to be exactly equal to n? Well, if we can find some orbit that has size n, we'll be done, right? Because then we can't get back in smaller than n steps. And that's easy to do. Look at the following bit string. The one that's just your k1s to start with, and then your n minus k zeros to end with. If you think about it a little bit, this isn't going to get back to where it starts until you've done the full rotation, because you grouped everything in that order. So this applies for this one, that the ith rotation of B is not B or I smaller than n. And so we're done. That's close, right? Everybody happy with it? Yeah, great. Excellent. What about B? Well, B is really simple now that we've done A, because think about it. So suppose the orbits are O1 through OL. Then how do we get the order of rotation? Well, you have to do something so that all these orbits get back to where the very first element. What's the smallest thing that will do that? The least common multiple of their sizes, right? For each orbit, you get back to itself if you do that size, and the smallest thing, therefore, is the least common multiple. So this is just the least common multiple of the sizes of the orbits. But wait a minute, from part A, we know that there's all the orbit sizes divide n, and there's from part A, we know that the order of the rotation is n, right? This is in the non-trivial cases, and you can check the trivial case easily. So from what we proved in A, this thing has got to be exactly what we claim it's going to be. And so this is if the order of rotation is this least common multiple, and we know from part A that this is going to be n in the non-trivial cases, then at least these guys have all got to divide the least. So the result follows. Questions? Any questions? Great. Okay, so I'm now going to want to talk about trying to find a homomesy. And I want some notation for that first. So a little bit of notation here. If I have a statistic and I have any subset y of x, then I'm going to use st of y to stand for the sum of my statistic over the elements of big Y. So it's just going to be the sum of the statistic values. So here's the statistic that I want to look at. Very simple statistic. I'm going to call it phi for first. So phi is going to be a statistic on BNK just to 0, 1. And you get it by just looking at what the first element is. Phi of a bit string, 1 through Bn. It's just the first bit. Let's go back to our example. So remember, here were my orbits. So what is phi of this orbit? Well, we have a 0 for this one, a 0 for this one, a 0, a 1 to begin this one, and a 1 to begin with one, for a grand total of 2. Yes, DJ has the right number of fingers. So therefore, what's the average? It's 2 over the size of the orbit, which was 4. That gives me a grand total of 1/2. Okay. Well, let's do it for the second orbit. It's going to be the sum of phi on that orbit. Yes, exactly. 1, right? Because it's 0 for the first one, 1 for the second one, and that's 1. And therefore, if I look at phi on the second orbit divided by its size, I get the same thing. That is not an accident. We have homomesy. Let's see why we have homomesy. the proposition. Phi on B and K, and I'll tell you exactly what it is. That's constant is K over N. It's K over N messic. So that, right? Yes, Maria.
Wasn't phi just like the number of ones that you get in the beginning, and then don't you want like phi over the total size of the orbit as your statistic? So it seemed like
I
the
don't
thing that was
understand your
constant.
question.
The thing that was constant was the 1/2, not the like total of the. The phi was like the total of the first entries. So isn't it that phi isn't mesic, but phi
Oh, I
over
see- I
the
see what
size of the
you're- I
orbit
think I
is the
see what you're saying.
statistic that is k
So
over
it's
n?
it's a
That's
it's we should say rotation. Yes, that'll fix what.
Okay, sure. Yeah, I just thought that the phi statistic
Yeah.
was not the one that was actually mesic. These you had 2 in the first orbit and 1 in the second orbit for the value of phi.
Yeah,
Right?
but to say mesic means that if you evaluate the average of the statistic.
Ah, okay. So
Right.
then phi is mesic. Yeah, I think I forgot
Yeah.
the original definition of homomesic. Yeah.
Exactly.
Okay, thanks.
Okay. Did that everybody else clear that up? Okay, wonderful. Let's prove it. So this is very easy proof, but it's going to give us a very important tool. So consider an orbit. Oh, okay. By the proposition we just proved, proposition 1, in fact, the first part of proposition 1, we can form from this orbit what I'm going to call, actually, which is called in the literature, a superorbit. You put a little cape on it and then you send it out into Gotham City. No, different kind of super here. So what's the superorbit? And I'm going to call that O star. The crucial thing about the superorbit, it's going to be of length n always, right? The orbits can be of different lengths, but these superorbits are all going to be of length n, because remember, we showed that the size of the orbit always divides the size, it divides n, so we can just replicate the orbit enough times to get it into, and I think, did I want proposition? I'd have to go back and look, which I'm not going to do. Maybe this should be proposition 1b. Let's just say proposition 1. That way I'm not. So just to write that down, what I just said, by repeating the given orbit.
Bruce, I think there's a question. Somebody
Yes,
raise hand button.
Yeah.
So these superorbits are multisets?
Remember, an orbit here is actually an ordered, right? Because you're always acting on the thing by rotation. So it would be a multi-set if it were a set, but it's actually a sequence. Orbit is a sequence because you're always acting on it by the thing. Yeah. So it's a sequence with repetitions.
Okay.
Other questions? So by repeating given orbit O by m times, where m is just n over the size of the orbit, right? That if you repeat an orbit of length, it's cardinality of O, this many times you get an orbit of length n. And just to make absolutely clear, let's go back to our example. What would O1 star be? Remember, O1 was our orbit of length 4. What will this one star? It's just O1, right?
Yeah,
Nothing is going to change. It's already of the maximum length. We don't need to do anything with it. Okay? So, right, so it'll look like 0, 0, 1, 0, 0. What about O2 star? How many times are we going to need to repeat O2 star to get the orbit? Twice, right? Because it was half as long. So it's going to be the ordered pair O2, O2, which is going to look like 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0. Everybody clear how these superorbits are formed? Any questions? Great. Well, but we have to worry, have we done anything? Have we changed the average, right? That we're crucially, no, we have not. Let's see why we have not changed the average in this. So note, what is the size of phi on the superorbit over the cardinality of the superorbit? Well, I think it should be pretty clear. How do those relate to the original orbit? You just repeated the original orbit m times, so you're going to also repeat whatever statistic you are m times. So that's just going to be m times the statistic on the original orbit over m times the cardinality of the original orbit. And the m's cancel, and you have not changed averages. The average is the same. Okay, so we can work with superorbits. We don't have to worry. Everybody happy with it? Okay, so, but now think about superorbits. If I have a superorbit, what's going to happen to each of the ones? Each of the ones is going to appear at the beginning exactly once, right? Since you're going through the whole thing. So since each of the k ones appears exactly once, as a first element. Star is average. Cardinality of O star, right? We're going to get, it's going to be 1 k of the times for those k1s, and then it's going to be 0 n minus k of the times for the rest. And what was the length of the orbit? It's always n, right? Because it's a superorbit. So that's for n. Well, add k1s over n. That gives you k over n. And I think we're done. Questions about this? Great. So, yes, Aditya.
Is it possible to think of superorbit as we label the ones and then make the orbit out of those?
Yes, if you wanted to consider the orbits as the ones as distinct, right? First one, second one, or whatever, you could also use that same sort of word. Exactly. Yes, Maria.
Yeah, so actually just as organizer, it's 8:43 right now, and you just finished up a proof. So I was wondering if it's a good time to take a 15-minute break, or
No, it's not.
okay, sounds good.
I'm keeping track of the time, Maria. You don't
Oh, okay, sounds good.
So yeah, I want to say one more thing, and we got started a little late, so it'll probably take us to about 10:50.
That's fine. Yeah.
So the other thing I want to say is, well, what was the other big thing we were looking for? We were looking for the CSP. Does this have a cyclic sieving phenomenon associated with it? So let's check. So what's one easy way to find, right? We need a polynomial for the CSP. What's an easy way to find a polynomial? Well, our statistic has what is its value? 0, 1, 2, 3, etc. Those are the possible powers of Q. So you could just use the generating function for that statistic. So we're going to consider, in general, and in particular on this case, we can always consider as our polynomial the sum over all x and x, q to the statistic value. Right? That gives me this polynomial. Let's see what happens here. So going back to B42, what is f of q going to be? It's going to be the sum over all these bit strings of q to the phi of b, the first element. And if you remember back when we did the calculations, we had 3 of the bit strings that begin with 0 and 3 of the bit strings that begin with 1, right? So this is going to be 3 times q to the 0 plus 3 times q to the first, or 3 plus 3q. Right, so that's my polynomial. Great. So now look at the group that we're looking at. We're looking at the group generated by rotation. And in this case, what was the order of rotation? The order of rotation was attempts to get the right number of fingers in the air. 4, right? We had a 4 cycle and a 2 cycle. If we do everything 4 times, that was also the proposition. So remember, we have to look at the corresponding roots of unity. So what are the corresponding roots of unity? So the 4th roots of unity. I squared, which is -1, and I cubed, which is -I. So now we have to check. Remember that we had this thing that we were trying to, we want to know whether the cardinality of fixed points for any g is gotten by plugging in a root of unity into my polynomial. Okay. Remember, the constraint here is that these two have the same order, g and omega. And unfortunately, this isn't going to work. And let me show you why. Well, let me show you one where it does work, but there's another value where it doesn't. Suppose we take as our group element the 0th power of rotation. Don't do any rotation at all, which is, think of that as the identity element. What would be the corresponding omega? What's the root of unity of, yes, 1, right? We want something of the identity element for the roots of unity here, the identity element for the rotation here. Well, what's the cardinality of the fixed point set? Well, how many things are fixed by not rotating at all? Yes, I see the right number of fingers up with Robbie, right? Everything's fixed. So this is just the cardinality of B42, which was 6. What happens if we plug in 2, 1 into my polynomial? Well, we get 3 plus 3 times 1, and that's 6, and everything is looking lovely. But now let's consider G being just a single rotation. what's the corresponding omega gonna be? I, right? This has got order 4, I has got order 4. How many things are fixed by just rotation? 0, exactly, Ben, right? In order for something to be fixed by a single rotation, it would have to be a fixed point of the group, and we didn't have any orbits of size 1. But what happens when I plug I into this polynomial? Are these equal? No. Oh, psi. So we will fix this after the break. That's what I want.